Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley, and this is the 22nd module in a series that we're recording to support the course EE221A, which is Linear System Theory at Berkeley. This module is about the Cayley-Hamilton theorem. And the background for this is it really comes from our knowledge that in order to compute solutions to linear differential equations, time-invariant linear differential equations, and to analyze the solutions and to think about control, we need to be able to have good ways to compute solutions to functions of a matrix. So in particular, the function that we've been looking at in the previous module is the matrix exponential e to the at, where this is the exponential function where in the exponent is an n by n matrix A. And so we know this is important because we have our general form of our solution to the system x dot equals ax plus bu is given by e to the a t minus t0 x0 plus the integral from t0 to t of e to the a t minus tau b u at tau d tau. Okay, so what did I do here? I just took our general form of a linear time varying solution, and given that we know that in the time invariant case, so when we have that the matrices A and B do not depend on time, so A and B do not depend on time, then the solution to that differential equation, when you start at some initial condition, which is x0, is given in terms of the state transition matrix, which in the time invariant case is given by the matrix exponential, times the initial state, so contribution from the initial state plus contribution from the input. So here you see the convolution between the state transition matrix and the term that depends on the input into the system, the BU term. Okay, so in order to understand how these solutions vary as the matrix A varies, we have to understand how to compute e to the at. And our technology for doing that is, as we recall from the last module, is computing the inverse Laplace transform of Si minus A inverse. And we talked about why that's problematic in general. So what we would like to do is to try to figure out ways to, even though we're going to use this format, to simplify the computation. And we'll do that by thinking about how to simplify the matrix A, how to perform a similarity transform on A so that we get it to a simpler form where it's generally easier to compute the matrix exponential. Okay, and so the first tool that we're going to discuss in this sequence is called the Cayley-Hamilton theorem. Cayley-Hamilton theorem. So to set up the Cayley-Hamilton theorem, let's first of all go back to let's sort of think about what we actually want to do, which is to compute in our matrix exponential Si minus A inverse and then take its inverse Laplace transform. Okay, so Si minus A inverse. So this is an n by n matrix, and we're taking its inverse. We know that in general, for the formula for taking an inverse of a matrix is the following. So it's the adjugate, not the adjoint, but the adjugate of the matrix, Si minus A, over the determinant of Si minus A. The determinant of Si minus A gives us the characteristic polynomial of the matrix A. So the determinant of Si minus A, we know it's an nth order polynomial, and we would have to compute it in general for a matrix A. But let's just represent it in terms of an nth order polynomial in S, and we'll use the coefficients di to represent the terms, the coefficients of the characteristic polynomial. So let's represent it as Sn plus d1 s to the n minus 1, etc., plus dn. Okay, so we usually use this terminology, chi hat A of S, to be the characteristic polynomial. Characteristic polynomial of A. Okay. The adjugate, on the other hand, so this is a polynomial. The adjugate is, so it's a scalar polynomial. These di's are scalars. The adjugate is a matrix, and I actually don't really care at this point what it looks like, but I'm just going to represent it as a matrix. And it's going to be, just from our computation of what the adjugate is when we're computing inverses of matrices, it's going to be a matrix of degree with terms in it of degree up to s to the n minus 1. Okay, so I'm going to write it as follows. Some matrix, some n by n matrix B0 times s to the n minus 1 plus B1 s to the n minus 2 all the way up to B to the n minus 1. And I don't really care what these B matrices are at this point. They're just n by n matrices. Okay, so I more care about what the form of Si minus A inverse is. Okay, so we have that. So what does Cayley-Hamilton theorem, what does the Cayley-Hamilton theorem say? Cayley-Hamilton theorem says the following. It says that every matrix satisfies its own characteristic polynomial. So Cayley-Hamilton says that if you take the matrix A, this is this n by n matrix thing, and you plug it in wherever you see an s in the characteristic polynomial, so even here, this d to the n term is multiplied by 1, which is really s to the 0. So we're plugging in, so it becomes a to the n plus d1 s to the n minus 1. So the characteristic polynomial evaluated at s is equal to the matrix A is equal to the 0 matrix. So Cayley-Hamilton says that every matrix satisfies its own characteristic polynomial. Okay, so that says a to the n plus d1 a to the n minus 1 plus d2 a to the n minus 2 plus dn a to the 0, which is the identity, is equal to the 0 matrix. Every matrix satisfies its own characteristic equation. Okay, and we can prove this. We can prove it just using the format of that we've discussed, like what the determinant, what form the characteristic equation looks like. Okay, so let's prove the Cayley-Hamilton theorem. Let's look at this expression up here. And let's multiply both sides of that equation by Si minus A times the determinant of Si minus A. So I can rewrite that equation as the adjugate of Si minus A times Si minus A is equal to the determinant of Si minus A, which is the characteristic polynomial, times the identity. Okay, so I've just rewritten this equation here. And so now I can multiply this out. So I've got this n minus first order polynomial where the coefficients are matrices, and I'm multiplying it by this first order polynomial, Si minus A. So I can multiply that out, and then I can relate term by term. So I'm going to relate equal powers of S together. Okay, so for example, we'll end up with B0. So if we just look at that, the term in s to the n, it's going to be s to the n minus 1 times s. So B0 will be equal to the s to the n term over here, which is just the identity, because we've multiplied that characteristic polynomial by the identity. So basically, we're multiplying that out and equating like terms. So you get that B0 is equal to the identity. And then keep performing that multiplication. We're not going to do it here, so you can do it on your own. So that's the equating the term of s to the n. If you do that and multiply it out, you find the following. So B1 is equal to B0A plus D1I. That's equating the coefficients of the s to the n minus 1 term down to, we can go to the B2 term, but if we go down to the Bn minus 1 term, Bn minus 1 is equal to b to the n minus, or Bn minus 2 term, a plus Dn minus 1I. And then finally, we also have that b to the n minus 1 is equal to, or times a. So this is the final term in that equating like powers, is equal to dni, is equal to minus dni. So plus dni is equal to 0. Okay, so that's getting a little small at the bottom of the board. But essentially what we've done here is we've just multiplied out that polynomial and we've equated like powers of s. Okay, so we have, we can now plug in things and simplify. Let's actually erase all of our terminology here. So from this term here, we have a relationship for b to the n minus 1. And from this last equation here, so we have two equations in b n minus 1. So if we relate those together, so let's take this expression for b to the n minus 1 and multiply it and substitute it into this equation here. So let's take equation star, let's post-multiply it by the matrix A, and then substitute wherever we see b to the n minus 1a, we'll substitute minus dni. Okay, so that, combining those last two equations, gives us bn minus 2a squared plus dn minus 1a plus dni is equal to 0. So this is always the 0 matrix. Okay, that should be the 0 matrix here too. Okay, and now we step up and we go to the bn minus 2 equation, and we get an expression for bn minus 2a squared from that previous equation, simplify it, and plug it in. So we'll end up, we can sort of go all the way back the chain until we end up with b0, and we get to b0, a to the n, plus d1, a to the n minus 1, plus dn minus 1i is equal to the 0 matrix. But we know that B0 is the identity, so that just becomes the identity, and we end up with basically the expression that we want, which is that the matrix, we've plugged in the matrix A into its characteristic polynomial, and we end up with 0. So basically this is a proof of the Cayley-Hamilton theorem. It just comes from the structure of what Si minus A, what that matrix inverse looks like in terms of the adjugate and the determinant. Okay, so why is this useful? So Cayley-Hamilton is a very, very important theorem. It tells us that every matrix satisfies its characteristic polynomial. But it tells us that, given that, it tells us that this expression, so this expression always equates to 0. So it tells us that if we have a polynomial function of a matrix A, where that polynomial is of degree greater than n, then we can use this identity to simplify that. We can always use that identity to bring that polynomial back to something which is of degree less than or equal to n. Okay, so let's conclude today's module by talking about this sort of important use of Cayley-Hamilton. So what I'm trying to say is that Cayley-Hamilton tells us something immediately about polynomial functions of matrices. And that's the following. Okay, so in general, we're interested in the matrix exponential, which is so we have its infinite series representation, but it's more complicated than a polynomial function of a matrix. But we're kind of building up to that by thinking about polynomial functions of a matrix. So if you had two polynomial functions. Let's call them, let's write them in terms of the variable s. So p1 hat of s and p2 hat of s. Those represent two polynomials in s. They're polynomial functions in s. And let's take each of those polynomials and let's divide through by the characteristic polynomial of the matrix A. So these are two polynomials. I don't care about what their dimension is. It could be less than n or greater than n. But what I'm going to do is take each of them and I'm going to divide through by the characteristic polynomial of the matrix A. And I'm going to write that division as some quotient plus some remainder. Okay, so what I know is that this polynomial is of degree n for an n by n matrix A. So it tells me that the remainder is going to be of degree less than n. Okay, so that's what I know here. So basically what I've said here is I've taken that polynomial and I've factored out the characteristic polynomial through this quotient representation. So equivalently, I could have just written that. And so let's do that with both of them. P2 hat of s divided through by the characteristic polynomial. We'll call that quotient Q2 plus R2 hat of s over chi hat A of s. Okay, so as a result of Cayley-Hamilton, what that says is that even if those two polynomials are not equal to each other, so even if P1 is not equal to P2, if the remainders are the same, if R1 hat of s is equal to R2 hat of s, then P1 of A is equal to P2 hat of A. And you can see that immediately because if you look at P1 hat of A, that's going to be Q1 hat of A times chi hat A of s, which is equal to 0. So that quotient term, the term which is the quotient multiplied by the characteristic polynomial, goes to 0, and P1 hat of A is equal to R1 hat of A. So even if these two polynomials are not the same, if the remainders are the same, then the polynomials evaluated at the matrix A are the same. And so what we're using this for, what we can use this for now, this very neat result, is that so this tells us that every polynomial function of A can be written as a function of powers of A up to A to the n minus 1. Okay, so that's the final thing that Cayley-Hamilton has said to us. Thus, this result tells us that every polynomial function of A can be expressed as a polynomial in A squared up to A to the n minus 1. Okay, so if you have a polynomial function and you plug in A and it's of degree greater than or n or greater, you can always simplify it to a polynomial function of A in these terms only. And that's the result of Cayley-Hamilton. Okay, so the key result of Cayley-Hamilton, we'll recall, is just that the characteristic polynomial of the matrix A evaluated at A is equal to 0. Okay, so that's the important result, and its implication is that you can use it to simplify polynomial functions of the matrix A. Okay, how we'll use this, we'll see as we move on to think about more general functions of matrices. Thanks.